7:05 for people that might still want to join. Okay, I guess we can get started now. Can anyone hear me?
Yeah.
Okay. Let's check the button. Okay, so I just want to start off with last week's question. There were some things I forgot to mention. Like from the question he gave us for that year, let me just scroll back to the part where we stopped. Um, okay. So basically, I've seen it what I'm looking for. From the memory mapping, he said the code segment starts at 0100, which we did, which we did here. This is where the code execution starts from. These are for the parameters. But he also said something about um execution starting from 0100. So by default, if you don't specify where your simulation is going to start from, and you just run like assemble, it's going to start from 0000. And during that last class, I had to like manually change it to 0100. But from what he said in the last class and from the textbook, the way you can programmatically set where your simulation to start from, and the directive we're going to use for that is this begin directive. So you can just set it to 0100, and anytime you run assemble, your code execution is going to start simulating from 0100. Please, if someone raise up your hand, you can ask your question. I'm not going to be on the Google Meet window.
Okay, it's not a question. Bolu just messaged me now asking if you could give like 10 minutes for him to break their fast before they could join us.
She would have mentioned that before we started now.
I'm just
Uh,
in between like maybe 7:15. I don't know.
so do you want to stop the
That's
recording or what?
you. Well, that one will just be there like that. Maybe okay. Since you are explaining something from the previous question, maybe you can just finish down before you go to what you want to do for today.
Let's just stop. Let's just stop. I'll start again when they're ready. So what time?
Okay.
7:20 or
Uh,
7:30? I don't know.
that was at I think 7:15. But she messaged me at like 7:05. So
So we should wait till 7:15.
yeah.
Okay. Let's wait then. Yeah, Kunle, can we continue now?
Yeah. I'm continue now.
Okay. So as I was saying, we're going to pick up from where we stopped last time around. And I said that the part of the question that I didn't consider, and the part I was referring to was where let me open the question. So in the memory mapping, they said the code execution should start at 0100 and code segment should also start at 0100, which is what we did here. But when you assemble your program by default, code execution starts at 0000, which is this. So if you don't specify anything in your program, you're going to start at 0000. And when we're running the program, then you have to like manually adjust the value to 0100. But there's a way you can, let me change it back to 0000. There's a way you can programmatically tell the program to start from 0100, and that will be with the use of the begin directive. So from the documentation here, you can see the directive's name is begin, followed by the address you want the code simulation to start from. So what we are going to do here, I'm just going to add a few lines here. So we specified the code execution should start at 0100. So we can also specify the code simulation should start at 0100H. So we can just say code simulation starts at 0100H. And if we come back to the file, okay. If we come back to the file, we also scroll down and see that you can also specify the end of the simulation with the end directive. So the end doesn't accept any address. You just specify the end. So the way I'm going to do that is I'm going to come back to the program, and at the end of the program, I can just put end here after my subroutine. So I can just put end here. So let's try to assemble the program now. If you assemble the program, you can see it automatically starts simulation from 0100. And if we were to pass in our radius and height from the last time, then just specify a radius of 2 and a height of 2. Then run after time, we get the same result as before. So to verify that, you can come to the memory address where we stored our parameters and our result. You can see this is the radius, this is the height, this is the volume, then 19 0, 0, 0 to 0, 4, 0 to 0, 4 maps to the fractional part, which is 19 in hexadecimal. Oh, sorry, this is 0 to 0, 3. 0 to 0, 3 is the decimal part, which maps to 19 hexadecimal. And 0 to 0, 4 is the fractional part, which is 1 as well. So another thing I also noticed is that somewhere in the book they said you can also specify your input as decimal or binary. So it doesn't necessarily have to be hex. When you're storing it in memory, it's going to be converted to hex. But when you're like using it in your program, you can specify it to be decimal or binary. I don't know if I can find that quickly here. Okay, this is it here. So they support binary number entry format. It is indicated by a B at the end of the value. So they also said the number of digits must be greater than 4 to prevent confusion with the default hexadecimal mode. Same thing for decimal, but is going to be indicated by D. The hex is the normal one we have been used to. So if you don't even specify anything at the end of the value, you're just going to assume it's hex, like they said here. Let me see. Okay. So to specify hex, the value followed by H, or even if you don't include the H, it's just going to assume it is hex. So if you want to specify binary or decimal, it's compulsory you put B or D. If not, you're going to assume it is hex. So for that question, we know that the numerator of pi is going to be 22. So instead of specifying 22 in hex, you can optionally specify 22 in binary. Instead, it should be at least 4 or more numbers so that it doesn't confuse it as hex. So that's why I added the extra zeros. Then you can also specify. Yeah.
Sorry for interrupting you. I just wanted to ask, does the end directive differ from the regular halt command? Isn't it like the same thing we're trying to achieve?
No. The end directive is regarding the simulation. So the halt is just like pausing or stopping the execution of the program. But the end directive is strictly for the simulation to indicate that we're done with the simulation. Let me just scroll back up. To end of assembly places the mnemonic at settings, stop simulation at that. So you can even decide to stop your simulation before you get to the end of the program if you just want to simulate a specific part. So the end directive is for simulation, halt is for ending the program or stopping the program. You get?
Yeah, thanks.
So I can also specify 7 as my digits for this guy. If I assemble it now, I should still get the same result. I should still get the same result. But in memory, before I even run it, if we were to check memory, we would see that it's still converting the 22 with past in decimal to hex in memory for storage. Same thing for 7, but 7 is the same in hex and decimal. That's why you can't tell the difference. But when you're accepting input, you can specify it in decimal. But when it is stored, it's going to be stored in hex. So that's just something to look out for. So if I assemble now and I pass in my arguments of radius and height, I should still get the same result. So still 0, 1, and 19. And also, one other thing I thought I should mention was there's a number converter tool here. You can convert between hex and binary and decimal without using your calculator. You can just say, let's say you want to convert 22 to hex. Just specify 22. It's going to give you the equivalent hex and binary digits, or you can do it from the hex part. Let's say you want to convert FA, you're going to convert it to decimal and binary. And for binary, you have to make sure it's at least 8 bits since you're going to be converting it to hex. So if you have something like 11101010, then it's going to convert it, and you're going to get the equivalent hex and decimal numbers. So I think I've included end. Yeah. So that's
Sorry, please. This what you just explained now. Are we supposed to use that to confirm our answer, or what's that for?
It's not necessarily to confirm your answer per se. I'm just letting you know that if you want to like perform conversion, you don't necessarily have to use your calculator if you're converting between hex, binary, and decimal. You can just use the converter tool there. You get?
Yeah, thank you.
Okay. So before we even go into the let me close this. Before we go into the PQ for 2024-2025, I just wanted to quickly cover stacks. I remember Hisham was saying something about learning how to call or how to use the call command. How will I put this now? Learning how to call a subroutine without using the call command. So that's what I'm just going to try to show here. So let me quickly open this thing again. So I'm just going to implement a simple subroutine that we used last class, which is multiply. To multiply finds the product of two numbers. I'm going to store the multiplicand in register B, multiply in register C, and I'm going to define the multiply subroutine. So a subroutine is just a function that you call. So here, what I want to do is I'm going to first ensure that the content of the accumulator is 0 by performing the XOR of the accumulator with itself. Then I'm going to add B to the accumulator C amount of times, like I explained last class. Then we do this until C drops to 0. And this is where our loop is going to start from. Once we are done, then we return and we can halt here. So if this works as expected, by the time we are done, the result or the product should be in the accumulator. Let me just run and see. Something is up. Move to oh, this should be hot. So this should be hot. Okay, that's the accumulator is showing 0, 0. Something is still wrong. Let me step through the program. So please.
Multiply.
Oh, I didn't call it. Yeah. So you call multiply. So if we were to step through the program line by line, you can kind of map out what is happening when you use call multiply. So I'm just going to move through it line by line, and you can see what is happening under the registers BC and also under this part that has to do with stack pointer and the rest. So the first thing you should notice is program start at 0000, and our program counter is pointing to 0000. So our program counter is basically just a register that points to the next instruction to be executed, and it is it stores addresses basically since it's a pointer. So if I move step by step now by pressing it once, okay, that's to start the simulation. If I move forward once, then you can see our current instruction is 00 and 0000, and our program counter is pointing to 0002. The reason why 1 is not the next instruction is because this move B05 is a 2-byte instruction. So it occupies 2 bytes in memory. And to know the number of bytes that the instruction is, you can just count the hex code or the number of hex code that are associated with this instruction. But like this move B05, these two are associated with it. Move C03, these two are associated with it. Then call multiply is a 3-byte instruction. So these 3 bytes associated with it, and halt is just a 1-byte instruction. So that's why we're skipping 1 and pointing to 2, because the first instruction is a 2-byte instruction. And if you notice, B has been stored as 5, or 5 has been stored in register B. So we move forward again. We're now on address 2. C has been stored, 3 has been stored at register C, and our program counter is now at 4. Now you observe what happens when we move to the next instruction, which is called multiply. Just keep an eye on the program counter. Like thinking through the program, like thinking in a sequential manner, when you move to 4, then the next instruction to be executed is meant to be 7. But let's see what happens. So let's move forward to call multiply. You can see that the next instruction is not 7. Next instruction is 8, which is the starting address of our multiply subroutine. And we can see that the stack pointer has changed from 0000, which was representing the base of the stack, indicating that the stack was empty, to FFFE. So basically what happened is that the stack pointer has been decremented by 2. If we were to perform 0 minus 2, and convert the result to X, you're going to get FFFA. I don't know if this thing can represent minus 2. I've not tried it before. It seems the only works positive. numbers. But basically, you perform the two's complement. So let me just open a note here. So two in hex. Since we are using a byte, we are going to have like extra zeros at the start. So that's 0000 for the first nibble and 0010. So this is basically 2 in hex 02. So to perform two's complement, you first perform the ones complement. Ones complement, you're just inverting all the bits one by one. So that will turn to 1111, then 1101. Then you add 1 to the ones complement. That's going to result in 1111, 1110. And if you were to convert this back to hex, you would see that the result is going to be FFFE. FFFE. The reason why this is change 00 is because it's treating it as a positive number. But when you invert the bit, you would know that this 1111 maps to F and 1110 maps to E from binary to hex. So basically, when you call multiply, we are decrementing the stack pointer by 2 and we are jumping to wherever the subroutine was defined. So if we move forward now, the next instruction to be executed will be the starting address of the subroutine. So this works as normal. So a way to replicate that behavior, I'm going to start with this call multiply is, we know that when you want to call a subroutine, we need to keep track of the next instruction to be executed. And I also forgot to show something. Let me just go back to that point. The reason why this stack was decremented was because something was pushed onto the stack. So by default, if you don't specify the base of the stack, then the default base for this simulator is FF. Basically the last address, FFFF. So by the time you decrement, we are all the way down to FFFE. Okay. So we would see that this value 7 that is stored is actually 0007. But remember, I was saying something in class about little Indian or something. So little Indian just means that the lower nibble is going to be pushed to the stack first. And the lower nibble is the upper nibble, the LSB. Give me a moment, please. So basically, the upper nibble is going to be pushed to the stack first, followed by the lower nibble. So this 00 comes first, then the lower nibble is then pushed as 7. So you are going to be reading it from the end of the stack towards the beginning, and the stack addresses go from like higher addresses to lower addresses, while the heap goes from lower addresses to higher addresses. So the reason why our stack pointer changed was because we moved the next instruction to be executed. It was 7, that's the return address. We moved it onto the stack. So with this information, we can then try to use like push and pop to replicate this behavior. So let's say we get rid of this call multiply. What is going to happen is, first, we know we need to store the return address. So let's first label the return address. Let me call it return address, which is halt. That will be the next instruction to be executed. And to push to the stack, there's a command called push. So the way it works is you use a register pair B, C, D, E, or HL. You push whatever you want to push to the stack, or you save whatever you want to push to the stack in the register pair first, and then you push whatever is in the register pair onto the stack. So to use the BC register pair, okay, I can't use BC. I'm already using B and C for my multiplicand and multiplier. So let me use DE register pair. To make use of the DE register pair, you can just call push on D, and it's going to take the values of the DE register pair and push it onto the stack. But currently, if you look at the values here, they are empty for now because we have not yet provided what should be stored on the stack yet. And the way we do that is by loading we load the return address onto our D register pair and we then push it onto the stack. So you have to load it first before you can push it. And the way we can do that is by load immediate D. So this controls the D register pair and can specify return address. So what is actually pushing is the address, not this return address. This return address is just like a variable that contains a value. So if I were to assemble this now, this return address will just be 0008. That's basically what is happening. So we load the register pair, then we push it onto the stack with the push command. So let's see if that part works for now. So let's step by step move through the program. Initially, we store 5 in B, 3 in C. Then let's look at the D register pair now. By loading immediate D, we have 0008 in the D register pair, which maps to the return address we have here. So what we then want to do is we want to push this value onto our stack that is still empty. So the way to know if the stack is empty, just look at the stack pointer. If it's 0000, the stack is empty. Then let's push forward. We push it onto the stack. So the stack is no longer empty. And if we want to verify the value is actually there, we come here and we can see 0008 has been stored on the stack. So now our stack contains the return address, but how does the program know where to go to exactly? That's where the jump command comes in. So we're going to use an unconditional jump to our multiply subroutine. So we're actually jumping to the address that is labeled by this multiply statement. And that would be 000C. So let's run through the program and let's see what happens. So we store 5 in B, 3 in C, then we store the return address in the D register pair, push it onto the stack, and we jump to the multiply subroutine. So it looks like that works so far. So from here, we can see that the next instruction to be executed, as shown by the program counter, is the multiply subroutine, not this halt statement. So we move on to the multiply subroutine. The function runs as normal. What then happens when we return? When we return, what happens is that the value of the top of the stack is read into the program counter. Let me see if I can show that. So before we get to the return statement, what is the value at the top of the stack? The value at the top of the stack is 000B. That's the return address. So by the time we hit return, just look at the program counter. It's going to change to the value at the top of the stack. And the stack pointer is now at 0000, indicating that the stack is empty. So basically, return just basically reads the value from the top of the stack and sets that value to the program counter to indicate that is the next instruction you should execute. So if I were to run this program now from start to finish, it should behave as expected without using the call command. But we can take it a step further. Since we know that return is basically just reading the value at the top of the stack, which is basically popping the value of the top of the stack and resetting the stack pointer. We can implement that using the pop command as well. So we can just pop. What pop does is it takes the value at the top of the stack and stores it in the register pair you specify. But for the pop command, you have to pop it into register pair HL because there are some instructions that allow you to work with the stack using the HL register pair. So some of those instructions are XT, HL, which basically just exchanges what is at the top of the stack with your stack pointer. There's also SPHL, it copies the content of the HL register to the stack pointer. So these instructions are not available when you use like the register per BC and DE. So you have to use HL for this. So basically, when we pop, what happens is the value at the top of the stack is now stored in the register pair HL. So let's just verify that. Let me move step by step. So this is the end of the program now. So HL is still 00. We know the value at the top of the stack is going to be, let me just verify. The value at the top of the stack is going to be 000B. So when I pop it into HL, HL then contains 000B. But how do we know, or how do we tell the program to go back to 000B if we're not going to use a return statement? So there's another instruction for that, PCHL. I'm not sure it's here or is in this other. Let me first check if it's here. I'm not sure it's here. So it's not here. So now all the instructions that you can run with this simulator are in this help section. Some of them are also here. So let me just set for PCHL. So this is PCHL. So what PCHL does is it copies the content of the HL register pair to the program counter. So you know the program counter just indicates the instruction that we should run next. So by copying the content of the HL register pair to the program counter, we're telling the program counter to run whatever is at that address next. So if we do SPHL, it copies the content of HL to the stack, to the program, PCHL, it copies the content of PCHL to the, it copies the content of the HL register pair to the program counter. SPHL does something else. So let's move step by step through the program. 5 is stored, 3 is stored. Then we load register per DE with the return address. We push that return address to the stack. Then we jump to the multiply subroutine. We run the multiply subroutine. Then start running the multiply subroutine. We pop the saved return address into the register pair HL. So you can see register pair HL contains 0B. But the program counter is saying the next line to run is 13. Okay, PCHL. Let's see what happens when we move forward. So from PCHL, we copy the content of the HL register pair 000B to the program counter. So they now have the same value. And what does 000B represent? 000B just represents the return address. Then we move forward, we're back at where we left off, and that's the end of the program. So let's run this again, and we still get the same output. Is someone trying to speak?
Yes, please. I have a question.
Okay.
So now all the things that we're doing now, if we're giving like tests or something, we write the code and we run it. Like
Yeah.
how is it supposed to know that okay, like probably what we're going to submit? Is it just the code we're submitting, or how is it going to know that okay, everything ran like this, everything ran like that? I mean, I don't really even get that part.
Like based on the question that we solved last week, the PQ, from what he has been saying in class, it seems like it's probably going to give us an algorithm to run. So following the steps of the algorithm, I mean, your code should be a bit tailored to what it's expecting based on whatever it gives you in the algorithm. And for what you are submitting, you just said we are submitting the assembly code file, which is what we're working on, and the hex file. Like by the end of, okay, let me just quickly show how you get the hex file. I showed this in the last class, but basically you just come here and you save hex code. That's basically it. Save the hex code, and it's going to save it as the hex file. Then go to wherever you saved your hex code, copy your assembly code file as well, zip it together, and you upload to a server.
Sorry, why did you remove the .hex file formats when you're trying to save?
So basically, the program, let me just say the program is not intelligent enough to remove it. What happens is that the extension is going to change, and normally when you are saving a file, it's just the last extension. If you have something like .asm.hex, it's just going to treat the last extension, which is .hex, as the extension of the file. So if I don't remove it now, if I don't remove it, you see what will happen. So save hex code. Let me add it back. It was .asm before. So if I save the hex code, if I save the hex code and I come to, I didn't even notice where I saved it, but it should be under solutions or something. It's not here. Let me save it again so that I'll know where I saved it this time. So under 2023, 2024. Okay. So if you come here now, you see that the extension is .asm.hex, but the file name is actually, I'm sorry, the file type is actually a hex file. So just to avoid confusion when you're submitting, you can just, when you're about saving, you can remove the ASM or you save it as the ASM.hex. But before you upload, just rename so you don't confuse our lecturer. Just rename. But you have to copy it, otherwise complaining. So I would advise just save it as whatever it gives you. Then before you upload your file, you rename it to remove the extra ASM that is not needed. Okay.
Sorry, can you explain the pop part of the code again? My network was bad.
So basically what pop does is it takes the value at the top of the stack. Let me just quickly go to where it's going to execute. So if we check our memory and the stack, which the default location is at the last address, we'll see that the value at the top of the stack is read from right to left because you are storing the upper nibble first, then the lower nibble. You don't have to worry about the order of storage. It's the program that will handle it for you. But just know that the lower nibble is going to be stored first, then the upper nibble comes next. So 000B is at the top of the stack. So when you run pop, pop basically takes what is at the top of the stack and stores it in the register pair you specify. So the register pair I'm specifying is HL, which is accessed by pop H. So if I move on to that part of the code now, you'd see that what is at the top of the stack, 000B, is now in the HL register pair. So from the HL register pair, I can then set my program counter by copying the content of the HL register pair to my program counter. So by the time I run the next instruction now, 000B is going to be copied onto the program counter. So the program counter is now pointing to the saved address, to the saved return address, indicating this is the next line of code to run. By the time we get back there, we've hit the next instruction or have come to the end of the program. Do you understand?
Yeah, thank you.
I don't know if I should also mention this. There's also a way you can, how will I put this? Let me quickly check this thing. There's a way you can implement push and pop without using push and pop. And you are going to make use of this xthl command. So just like PCHL, xthl just copies the item at the top of this. No, it copies the item at the top of the stack into the HL register pair. Please let me verify that. I don't know if it's the other way around. XTHL is here. So okay, he exchanges the values stored at HL register pair with the item at the top of the stack. So the way this is going to work is, we know when we are pushing, due to the fact that our stack is going from higher addresses to lower addresses. So when we are pushing, what happens is, like I mentioned, the stack pointer is going to decrement by 2 since we are going from higher to lower. And the reason it's decrementing by 2 because we are pushing 2 bytes into the stack since addresses are 16 bits, that's 2 bytes. So if you know that pushing is just going to basically decrement the stack pointer by 2, and there's a way you can copy the content of a register onto the stack directly, then you can implement the push command without even using the push command. So what's going to happen is, before I push, I'm going to create space for the element I want to push onto the stack. And the way I'm going to create that space is by decrementing the stack pointer by 2. So we are going to be using DCX and not DCR, because DCR is for registers, DCX is for register pairs. So decrement, so this decrement, and the argument is going to be SP, the stack pointer. So you can access the stack pointer from your program. You decrement the stack pointer by 2. So, yeah?
Yeah, I don't think the screen is updating. Or
Are you sure it's not your network? Or is it my network?
is it? Susan was asking on the group chat, so I don't know. Maybe you know.
It is now. She's writing DC currently.
Yeah.
Oh, we're
Said
talking
my
about.
network.
It's in the lab network.
All right.
Yeah. So what is going to happen is, before you push that value to the stack, let me just comment out the push code I made. I think I pushed the. So before you push to the stack, you create space for that element first by decrementing the stack pointer by 2. So decrement SP decrements by 1. Do it again, it decrements by 2. So we know the XDHL exchanges the content of the HL register pair with the item at the top of the stack. So if we can initially store our address in the HL register pair, by the time we exchange it to what is at the top of the stack, then that address is going to be placed at the top of the stack. So now I've created space for the element that we want to push. So let's just verify that I'm not going to run it in full. So let's just go to decrement SP. So it decrements to FFFF and decrements to FFFE, like when we were calling push. So since we are going to be using XDHL, it only works with the HL register pair. So we have to load our address, the return address, into the HL register pair, not we can't interact from there. So we have our address in the HL register pair. What do you want to do with the address? We want to place it at the top of the stack. So to do that now, since we've created space for it, you can just do XTHL. So it swaps the stack, not the stack pointer, it swaps the element at the top of the stack with the HL register pair. So let's run it. So we first push 5 to B, store 3 in C. So HL register pair now contains the return address. You can see the return address has changed because we added new lines of code. So the return address is 000D now. So it's stored in the HL register pair. And if we check here, we can see the stack is originally empty. So by the time we swap, whatever is in the HL register pair is going to be placed at these last 2 locations, and 00 is going to be placed in the HL register pair since we are swapping. So let's move to that part now. So decrement, and by the time we swap, we can see HL now contains 0000, and our stack contains whatever we swapped it with from HL 000D. So that's basically how to implement push without using push. Decrement the stack pointer twice. The reason why you do that, you're creating space for the element at the top of the stack. Then you swap it with the content of the HL register pair. But before you swap, ensure that what you want to place at the top of the stack is already in your HL register pair. So you can do the same thing for pop. If you remember from pop, let me just assemble it again to refresh. memory. For pop, what basically happens is, let me get it first. So pop, pop basically you can see we moved from FFFE for the stack pointer to 0000. So that implies we are adding 2 to the stack pointer. That's going to imitate removing the item from top of the stack. But we are not actually removing the item from the top of the stack. We are just resetting the stack pointer. So if the stack pointer is pointing to the base of the stack, indicates the stack is empty. But as you will see, when we decrement the stack pointer, it's going to contain that old value. But that is not going to matter because when we push to the stack, it's going to start from whatever the stack pointer is pointing at. So if the stack pointer is pointing at 0000 and we still have an old value in the stack, it is simply just going to overwrite that old value. It doesn't actually clear whatever is at the top of the stack. So for pop, what we are going to do is first, before we decrement the stack pointer, I want to first get a value before we lose it. So you first, we can't use pop. So we have to get whatever is at the top of the stack. So what is at the top of the stack can be obtained and placed in the HL register pair using XTHL like before. So let's run and see what happens. Okay, that's the next instruction. So where at the top of the stack, we see 000D. So HL register pair is zeros empty. So by the time we swap it with the stack, the element at the top of the stack, then we can see we have 000D, and HL that was 0000 is now 0000 in the stack. So that has got the value we need, but we need to like simulate removing that element from the stack so that we won't run out of we won't run into the issue of like stack overflow just because we copied an item from the stack, but we did not indicate that we removed the item. So that's to accomplish that, we just increment the stack pointer by 2 back to indicate we are done with the value we got from the top of the stack. So you can overwrite it if you need the space. So I'm going to increment the stack pointer twice. So if I increment the stack pointer twice, the stack pointer will now point back to the original position as if the element wasn't there before. So if I move through the program again, initially 000D is at the top of the stack and HL is empty. We swap. So 000D is now in HL. So to simulate popping from the top of the stack, we're just going to increment our stack pointer by 2 again. So by the time we increment our stack pointer by 2, it is back at the default position of 0000. So we continue the program and we are back to halt. Does anyone have any question regarding this stack explanation?
Would it also be possible for us to use the SPHL command or instruction to kind of achieve the same thing?
No, you can't use SP to achieve what exactly? Is it PC or
Yeah,
CHL?
if we were, I could just explain how to go about that push and pop operation using XTHL.
So, you know, XTHL, what XTHL does is swaps the element at the top of the stack with the HL register pair. But what SPHL does is it copies, if I'm not mistaken, it copies the content of the HL register pair to the stack pointer, copies HL to the stack pointer, not the element at the top of the stack, to the stack. It copies HL to the stack pointer. So it's not even going to replace the element at the top of the stack. It's going to replace the stack pointer itself. So how do I do this without interfering with this program? So let's just replace this guy with, no, let me use the first one so that the program will be shorter. Let me use the first one. So SPHL, let's see what happens. Store B and C, load the immediate return. So okay, before we get here. So stack pointer is FFFE. When we call SPHL, HL is containing what 000D. So it copies the content of the HL register pair 000D as the stack point. Wait, okay, that's the decrement. It copies the content of 000D into the stack pointer. So we're updating the stack pointer itself. What we want to update is what the stack pointer is pointing to. But if you use SPHL, you're updating the stack pointer itself, not the value. So this SPHL works with the address, that is the stack pointer, while XTHL works with the value at the top of the stack. That is what the stack pointer is actually pointing to. I don't know if you get the difference. You get?
Yeah, thank you.
Okay, so use XTHL. What's next? Okay. I think we can go on to the question for today, to the tutorial question. I need to save this. So this one, traffic lights, similar to the one he gave us on Thursday, but it's not exactly the same thing. So basically, consider the road layout that has the traffic light controller shown. The approaching vehicles to the zebra crossing is indicated with arrows in the diagram, with each lane having a traffic light display of red, yellow, green, using a transition diagram for the sequence of operation, starting from the top lane and moving anti-clockwise. Draw a truth table with the green light having an on state for 5 seconds, yellow light 2 seconds. From the foregoing, use the system and utilize the instruction set of the device, write an assembly language, blah, blah, blah. So the first thing is to minimize the number of output lines from A. So just looking at the traffic lights, we have 3 traffic lights, and the 3 traffic lights have, let us say, 3 different states. It can be red, yellow, or green. So if you want to represent those 3 by 3, that's 9 different states individually, we are going to need 9 bits. But due to the limitations of the processor, we can only use, or not even limitations, to optimize the process. Like I said, minimize the number of output lines. So you're trying to simplify the whole connection and optimize the number of bits you're going to use. So we have to reduce it from 9 bits one way or the other. And the way I did that is in the guide. Basically, we know that the red state is going to be dependent on the green and yellow state. So the traffic light only turns red when the green state is off, or when the green state is 0, or when the yellow state is 0. Basically, when the green light is off, yellow light is off, then red has to come on. So that behavior can be replicated using a NOR gate. And as I showed you, I just used the Morgans to reduce the number of gates from 3, not, and to just a simple NOR gate. So there are 3 traffic lanes around the zebra crossing. See, lane A, B, C. Lane A is the top lane, lane B is the bottom lane. Lane C is the right lane. So he said it's starting from something. Okay, starting from the top lane. That's why my own top lane is lane A. So you have to follow the order I gave in the question. Starting from the top lane, and moving anti-clockwise. So if we move anti-clockwise, let's say this is our top lane, we move anti-clockwise, then our next lane is going to be the bottom lane, which is our lane B. Continue moving anti-clockwise. Our third lane is going to be the right lane, which is our lane C. So each lane has a traffic light display of red, yellow, green. Okay. So green light has an on state for 5 seconds. Yellow light has an on state for 2 seconds. Red light has an on state. When the green light is off, yellow light is off for the associated traffic light. So the red is dependent on green and yellow being off. So the red light can be controlled using no operation on the green and yellow light with the help of hardware. So as we've eliminated the bit for the red, so we don't need any bit for the red light again. We only need bit for the green and yellow light. So we basically simplified the number of bits required from 9 to 6. So starting from the top lane,
Sorry, please. How did you not get to 6?
how did I get to 6? Because the state of the red light is going to be dependent on the yellow and green light. So basically, we are going to rely on the hardware logic to get the value of the red light.
So 3 bits per each.
Yeah, 3 bits each. So that's why we got from 9 to 6. So starting from lane 1 and moving anti-clockwise, the way I did mine is I'm starting from the LSB. So when lane A, that's the top lane, when the lane A is on the green light, then D0 is going to be 1. When lane A is on the yellow light, D1 is 1, while the others are 0. Then B is on the um, green light, D2 is going to be 1, the others are 0. Lane B, yellow light, D3, 1, others. Same thing for lane C, for the green and yellow part. So we're not going to be using D6 and D7 since you don't need it. You only have 6 states. You don't need to use all the 8 states. But to keep it simple, you can just assume D6 and D7 going to be 0. So this is truth table. For the first case, lane A green 00001, basically lane A yellow 02. This is the hex equivalent. Lane B green 04. Lane B yellow 08. Lane C green 10, and lane C yellow 20. So this is how the state diagram is going to look. We start from lane A green, which is 01, and we move anti-clockwise. Lane A yellow, lane B green, lane B yellow, lane C green, lane C yellow. So that's basically it. Then to write the code, open the file. Should be 2024, 25. Okay. So these comments are just basically explaining what I already wrote in the PDF. So this out 01 is just representing the output ports, basically. So like I mentioned last class, this is the input output port. So this first one is 00. The first 0 comes from the left, let's say, from this left column, and the other bit value comes from the top column. So this is going to be 00, 01, 02, 03, 04. This did not specify anything about where we should output the results. I just went with 01. So you can make it anything, but in your program or in your Kini, I even forgot to include it. When you are writing your reason for making it 01, you can just tell him you do not specify, so you assumed the output is going to be written out at 01. You can include that in your report too. So basically what I do is first I set the content of the accumulator to simulate lane A being green, that is 01 hex. I output the result in the accumulator to the output port 01. So this 01 is going to contain the value 0, 1. So let me just assemble around that part. 0, 1 is in the accumulator now. After we run the next line of code, we're going to get 0, 1. So for the delay subroutine, let me show you that the way you can create a subroutine like a delay, using a delay. So you come to this subroutine tab and insert delay subroutine. So there are different options here. The label is just the name, how long you want to delay for. So this is going to be in milliseconds. So if you say you should, let's say, delay for 1 second, then it's going to be 1000 milliseconds. So just note that your delay has to be specified in milliseconds. Then there's also something about maximum and minimum delay. So for this configuration, the maximum delay is 503 milliseconds, minimum delay is 0.130 milliseconds. So the way to get around that is by one, you can just increase the number of registers used. So in this case, we're using a register pair, 2 registers, either B, C, D, or H. So you can increase it to 3 registers, but I'm sure it's going to specify what you should do here. But if it doesn't, you can just go with the default options, except you need like a range that would satisfy the delay you're looking for. So if you say the range of you should delay for 1 second, this range of 0.13 milliseconds to 503 milliseconds doesn't include the range of 1 second, which is 1000 milliseconds. So one way to get around that, you can just increase the value of these T states. And you should note that this delay is not entirely accurate. Like I said, it depends on the speed of your computer. So let's say I change this from 310 nanoseconds to 380 nanoseconds. This program is buggy. So 320, you can see, okay, it was 320. I changed it to 350 basically. I can't control this. I don't know. It's just messing up. That's where the program is acting. But I changed it to 350 and you can see our range changed as well from 0.1427 to 550 milliseconds. So let me change it to like 3000. You can see our range has increased again from 1.224 milliseconds to 4718.571 milliseconds. So if we were to delay for 1 second, then this range satisfies the delay we are looking for. But another way you can do that is you can just increase the number of register pairs. So this one, the register pairs available are B, C, D, H, L. You can decide to use 3 registers, the B, C, D. So the more the registers, the higher you can count. You can see the range has already automatically increased from 0.02 to 74,000 milliseconds. So you can pick the registers you want to use here as well. And you can also set it to 1 register. You can set it to 2 registers. So it's going to be treated as 2 individual registers, not a register pair. And the last option is the register pair, which is the default. So let's say we want to recreate our delay for 2 seconds subroutine. Since it did not specify how we should set the registers for the delay, I'm just going to go with the default. And what I did is I just increased this in time for 1 T state. So you can see you don't have enough milliseconds yet. So let me increase it to 600. Still on 1000. So not enough. We're looking for 2 seconds. That's 2000 milliseconds. Okay, this is too much. Let me come down to, let's say, 1750 and 750. So the range of 2 seconds is included now since the max is 2752 milliseconds. So you can just say delay for 2 seconds and give it a name. I don't want it to do the same name I gave it before. Let us say D2, D2S. So by the time you save it, it is normally going to be appended to the end of your program. So this just simulates delaying for 2 seconds. So you can do the same thing for the 5 second one too. insert the delay subroutine, specify a label, let's say 5 seconds. Ensure whatever you're passing in here lies within this range. 5 seconds doesn't lie within that range. We're looking for 5,000 milliseconds. So you can just increase this guy. Still not enough. Okay, it looks like it's enough now. I use 3.2. It's not showing, but I use 3.2. Then delay for 5 seconds, 5,000 milliseconds, and it's automatically added to the end of the program. So once you have this, basically I've already done this above, so I can just get rid of this. Delay for 2 seconds, delay for 5 seconds. All you have to do is just call it in your program. So basically, we output the results to the output port 01 and wait for 5 seconds before we then change the value at the port. So this is simulating the traffic light being green on lane 1 for 5 seconds. So then after 5 seconds, we change the value at the accumulator to 02. This is for the traffic light being yellow at lane 1. Output the results to the port 01. Wait for 2 seconds. Same thing, go to lane B. Traffic lights on lane B being green. Output the results to the port. Wait for 5 seconds. After 5 seconds, make the traffic light yellow for lane B. Output the results. Wait for 2 seconds. Then after 2 seconds, make the traffic light for lane A green. Output the result. Wait for 5 seconds. After 5 seconds, make the traffic light for lane C yellow. Output the result and wait for 2 seconds. So at the end of the sequence, he didn't. I'm not sure he said anything about this, but ideally, just thinking about it, you wouldn't want the traffic light to work for like only one sequence. You want them to be working 247. So by the time we get to the end of the sequence, what I did was basically I just restarted the loop. So this is basically going to be an infinite loop. So if you assemble this thing, it's just going to keep running and running and running, and you're not going to see any results because it's running infinitely. As long as the program is executing, it's going to keep running. But to ensure our traffic light key is working, you can just comment it out for now. And like he said, I think he's actually less interested in the delay part because if you step program like line by line, it's going to take forever to finish counting down from this to 0. So when he's probably checking our code, he's probably just going to comment this part like he did in class out, and he's going to leave the return statement. So he's just basically testing for the logic of the program. And what this delay subroutine actually does is basically just a counter. It loads the BC register pair with 65B8, this is in hex, and it decrements the BC register pair by 1. Then move B to A. The reason why we're moving B to A is so that we can perform the OR operation. So basically, since we are using 2 registers, you cannot just do something like jump on node 0 to like end the loop when we get to 0. What we have to do is we have to compare the 2 values of the register pair first. So let's say we have register pair. Okay. Let's say we have in A we have 0101 1010, and in B we have 0000 1111. The only way to detect when we've gotten to 0 is when the OR operation between the higher register and the lower register results in 0. If the OR operation between these 2 registers results in 0, then it implies that our counter has reached the point 0. And the OR operation is basically just adding and ignoring any carry. So 1 plus 0, 1. Let me write it out. 1 plus 0, 1 plus 0. Let me start from the on the left end to avoid confusion. We're not dealing with carry, so it doesn't matter. 0 plus 0 is 0, 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 1. 1 plus 1 is 1. It's actually 1 or 1. When I'm saying 1 plus 1 is 1 or 1. Then 1 plus 0, 1, 1 plus 1, 1. 1 plus 0, 1. So the only case where we're going to get zeros, all zeros from the OR operation is when both registers are 0. So when both registers are 0 and we perform the OR operation between these two registers, then we've gotten to 0 on our counter. So basically, we are decrementing by B. We are moving the content of the higher register or the higher byte into the accumulator so that we can compare it to the lower byte. So if they are both 0, then it implies that our counter has gotten to 0. So by the time this condition is satisfied, our counter is at 0. Jump or no 0 is not going to jump because the 0 bit is going to be 1. And jump or no 0 jumps if the 0 bit is 0. So by this point, the 0 bit is going to be 1 and we return. So that's basically what is happening in the delay subroutine. Just load the register pair with, I don't know how it generates the values, but load it with some values, then decrement to 0. When it gets to 0, we come to the end of the delay subroutine. So that's basically it for this question. What's time? I don't know if anybody has any question regarding the first class, the stack explanation, or this one we just completed now. Any questions?
How about the
I can't hear if you're still speaking. I don't know if it's your network. Does anyone have any other questions?
Do you think that your explanation for like instead of using like call and multiply subroutine and just using function, do you think there's a way he can ask the question instead of just using multiply, like using the call subroutine, you should go back?
Like
Using
instead
like
of
just
using call,
the
Abby,
concept, try to use the concept like line by line. Yeah.
the reason why I even worked on the problem is because he mentioned it in class that we should learn how to call a function or be a subroutine without actually using for. So I don't know if something like that is on his radar for maybe certain questions, but he mentioned it in class, so that's why I learned it and that's why I explained it. But I don't know if he's going to set it. Yeah. Chi, do you still want to ask your question?
okay? Yeah, I think my network went back. I was trying to ask if you were or if you intend on covering the serial IU and interrupt talk itself. We had many different questions. Forgotten. But yeah, you want to do the talks.
To be honest, I'll need to revise this slide, so probably not today. I don't know if you can still meet before the test. Maybe T. When do we have this one? Okay, maybe Tuesday, like after Adetono's test. I need to revise the slide. Do you when we mean covering? Do you mean like I know there's still one more like based on the question he asked us to solve last class. But are you referring to the example he gave in that PowerPoint that he called SODSR or something, where he did serial transmission?
Yeah, I think that should be part of it.
Okay, and probably another time. I need to go through revise. I think we still have a bit of time. And I also recall Hisham saying something about reversing an array. I think it has been a while, but there's a way to reverse the items in an array. I just hope I still remember. So basically, you'll be given a block of data and they might ask you to reverse it. So the way you do that is, can I close this thing? Let me reopen it. So let me just specify the data first. So we're setting our starting address, our origin to, let's say, 6050. I can just pass in random data. So this data is our label. So what is actually stored at this data is going to be 12H, 34H, 56H, 78H, and 90H. So these are just random data. So if we were to asked to reverse this, how would we go about it? Well, for this, we can also make use of the stack. So let me just ensure this is loaded properly. So if I assemble, nothing is going to be shown here. But if I check memory and scroll down to 6050, then our input should be there. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So basically, the way it's going to work is, I don't remember how I did this thing. The way it's going to work is first, we want to load the address, the starting address into our HR register pair. So our HR register pair at this point is going to contain the address 6050. And let's say we want to copy the reversed array to a location, let's say destination. So destination is going to have an address that is equals to 6060, something that's below that we can easily compare. So the idea is basically to push all these items 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 onto the stack. And you remember, stack is the last and first out data structure. So what is going to be at the top of the stack is going to be the last thing we pushed. So if we push everything at this point, then when we want to pop, the first pop is going to contain the value 90. So let's first push everything. How many items do we have in our array? So we have 5 items. Okay, so let me just store the count in our register C. So just keeps track of the, let's say, array length. So using a loop, what we want to do is basically, we know that by default, let me remove this with our assembly. By default, whatever is being pointed to in the HR register pair is going to be stored in memory, this M register. So if I load the HR register pair now, 6050, where is our 6050? The first element here, which is 12. So the way I can access this 12, that's the value being pointed to from 6050, is just by reading whatever is at M. So you can treat M as a register like the rest of the registers, A, B, C, D, H, and L. So what I'm going to do now is I'm going to initialize my loop, and I'm going to basically get whatever is at M and push it. But M is a register and we need a register pair, so that might not work directly. So there's an instruction for loading a register pair with a value directly. Let me just check.
But haven't you already loaded to hit your register fields that data address?
The issue is what is at the HR register pair is the address. What I need is the value. So it's the value I want to push to the top of the stack, not the address. But thinking about it now, I think I can still push the address, but when I'm popping, what I'm going to be doing is using the address, I'm going to get the value using the M register. So I'm just going to push the address. That works as well. So I can push the address. Then
What
when I'm
about that's L use
LL
load and store with it.
that starts with stacks and LDAX.
Yeah, those ones with X are there.
And the thing with that one is would that work? Let me go to the help again. So basically what stacks does is just gets or fetches whatever is stored at wait. It fetches whatever is stored at, like in this example they use stacks B, whatever is stored at register pair BC, which is probably going to be an address, and stores that value in the address in the accumulator. So I'm not sure that it's going to work in our case. I'm not sure that it's going to work. And if it works, it might work, but I'm not sure it's going to be as straightforward as it's looking. So what I'm going to do is I'm just going to push the addresses onto the stack. Then when I'm popping from the stack, I can then use that address to map the value I'm looking for to the M register. So for this, I need to push uh I need to push H. Since H is containing my data, let me hold first and see what is going to be in H. So H6050, okay, as expected. But we need to do this how many times? We need to do this 5 times. So we increment H. So the next iteration, H is going to be 6051. And we decrement C. So if C is not yet 0, then continue the loop, start again. So let's see what happens. So initially, load the data into H, that's 6050. Initialize our counter, push H, whatever is at H or register pair, that's 6050, onto our stack. So let's check our stack now if we have anything there. So we have 6050. Like I said, the upper label goes in first, followed by the lower label. So increment H. H is pointed to 6051, which has the value 34. Repeat the process till we get to the end of the array. I think we're done. So let's check our stack. Our stack now has all the addresses 6050, 51, 52, 53, 54. So this instruction basically, this loop pushes all our value, the address of our values onto the stack. So now we need to pop them back. So by the time we are popping, we're going to be getting the last element first. So just by virtue of that, whatever we get is going to be in reverse order. So since my counter has decremented to 0, I want to reinitialize it to 5 to indicate that I need to pop 5 items from the stack. So by the time I pop H, let's see what happens. Let's see what happens first before I go further. So our loop runs. I'm not going to skip the loop parts. We have 5 in the register C. So by the time we pop H, 6054, it's 6054 the last element at the top of our stack. Let's check here. So this 6050, 51, 52, 53, 54. So yes, it's the last element and it contains the value 90. So that just proves that it's the last element. So what we want to do here now is we want to store this value somewhere. How do we store the value somewhere? we need to store the value at our destination. But we have not even initialized. We only gave the destination a value address of 6060, but I'm not yet assigned that to any register. What I'm going to do at the destination, I can just load my destination into register D. So register D is going to contain the address 6060 initially. So what happens is I want to copy my values from the source to the destination. So if I pop this into D, then D is going to contain the address 6060. But what we are interested in is actually the address. What we're interested in is the value, not the address. So how can we get around this? And the only way we can access the value is with the M register. And the M register is controlled by the HL register. So that means I have to pop this into H so that I can access it via M. I have to pop this into H. So let me just do a bit of renaming. So I'm going to use my D to push to the stack, and I'm going to use my H to pop from the stack. So let's run the code and see what we have now. She still work as intended, 6050. Okay. This should change to push D and increment D. Since we're using D now, so 6050, 6051. Let us get to the end of the loop and verify everything is on the stack. Everything is on the stack. Then we pop H. So by the time we pop H, H contains 90, which is what we need. So we now need a way to move this value 90 into the address we specified as our destination, which is 6060. And the way we are going to do that is basically let's move the content of the memory into register. So let's move the content of the memory into register D. So the content of the memory is 90. So by the time we move 90 into register D, no, we don't want to use the register. Oh, seems confusing. This is not what we want. This is not what we want. Check. Let me just open the code. I've written this thing before. I think the explanation would be better if I just walk through it. So reverse array. So let me open it from here. Let's do it. Okay, so I initialize this. Okay, this is my destination address, SPHL. I'm not sure this is necessary. Okay, basically I used here, what I did here is I set my destination address to D000. So let me just mark that as my destination. So destination equals destination. So my destination maps to, but I'm not going to make it C060 so that we can easily see where we copied it to side by side. So this is not necessary for this explanation. My destination is at C060, initialize my array length, and I set my data to be stored in register per HR. So this is basically just going to push everything that we specified here onto the stack like before. Then, like I mentioned before, you reinitialize your count to 5 since it has decremented to 0 here, and you load D with C060. Let me first make sure this code runs before I start trying to understand the taking. So C050 and C060, that's where our result is going to be. Okay, so it works here. Okay, that means it's correct. I'm just wondering why I set this to D000 initially. Okay. I remember. So basically, it's possible that Engineer Hisham can ask you to set the base pointer or like, yeah, to set the base pointer like where your stack should start from. Originally, if you don't specify anything, your stack is going to start reading from FF. So if he says he wants your stack address to start from a different location, one way you can handle that is by first loading the HR register pair with what would be your base pointer. So here I made my base pointer D000. So basically load HR with base pointer. Then I now use the SPHL command. So what the SPHL command does is copies the content of the HR register to the stack pointer. So if we were to run this now, assemble load HR with D000, then SPHL copies the content of HR register D000 to the stack pointer. Our stack pointer is initially at 0000. By the time we run SPHL, it becomes D000. So since our stack is still empty, then the new base of our stack is going to be D000. So the next step is just to initialize our array length, then load our HR register pair with the data we want to reverse. So our HR register pair points to or has the value 6050 and it points to 12. So we push everything to the stack like before. Push everything to the stack. Let's make sure everything is on the stack. And remember, we set our stack base pointer to be D000. So it should no longer be here, but it should be at D000. Oh, this seems so hard to scroll. D000. Okay. Yeah. So remember, we decrement first. We create space first by decrementing by 2 before we push. So the first element is going to be stored at CFFF. And decrement again, next element is going to be stored at CFFE. So that's why I'm starting from CFFF because we are decrementing first to create space for the element you want to push to the stack. So this basically just sets the base of the stack. So our values are on the stack now. Then how do we pop them? The way the pop part works is first you initialize account to 5 to indicate the number of elements you want to pop. And what I did here is I set my destination where I want to copy the reverse item to. So the starting address of that is 6060. So I then pop what is at the top of the stack. The value at the top of the stack is going to be the last item, which is 90 with an address of C054. So it has an address of C054. Yeah, this is the element at the top of the stack, C054. So I pop it into my HR register pair. If I go next, this changes to C054 and it is now pointing to 90. So this value 90 that is being stored at address C054, I then move it into my accumulator by using move AM. So I copy from memory and I move it into my accumulator. So 90 is going to be in my accumulator. I then use stacks. So the stacks too. Okay, stacks basically. Okay, what stacks does is basically it copies whatever is in the accumulator and stores it in the address that is represented by the register pair. I think this was the part I was missing out. Okay, I think that was what she was even talking about. So it copies whatever was in the accumulator and it stores it at the register pair DE. So DE contains 6060. So whatever is in the accumulator 90 is going to be stored at address 6060. So let's verify that. Let's scroll all the way down to 6060. Yeah, so 90 is at 6060. Already seen it. 90 is at 6060. Then we increment our D, our register per D. So D is now going to be at 6061. Then we decrement our account, continue the loop, pop what is now at the top of the stack, 6053, which contains the value 78, move it into the accumulator, and from the accumulator, we can specify that we want to store it at register per DE. Register per DE now contains 6061. So the value at the top of the stack, which is 78, is going to be stored at 6061. Increment our D, 6062, decrement C. So we have 3 more elements to pop and we start the loop again. By the time we pop again, what we have at the top of the stack is address 6052, which contains the value 56. So we move the value 56 into the accumulator and we store whatever is in the accumulator at address register pair DE, that's 6062. So repeat this process. Let me just go to the last one. So for the last one, what we have at the top of the stack is the first element we pushed, which is 6050, and that address points to the value 12. So we move 12 into the accumulator and we store whatever is in the accumulator at the address specified by the register pair DE6064. By the time we are done, we increment the decrement C. So we've gotten to the end of the loop since C is now 0, and we've gotten to the end of the program. So if we to check the memory now, we'll see that we've copied our values from 6050 through 6054, and we've reversed it and placed it at address 6060 all the way down to 6064. So that's one way we can reverse like a block of data using a stack. Does anyone have any questions? Any questions from anyone? Or we can end the call. Or the interrupt, like I said, I have to revise the slide. I didn't prepare for that. So maybe on Tuesday
What about the exercise that we did? What's the difference between that one and this one?
Which exercise? The one we did on Thursday, the traffic lights.
Yeah, the one we did in class. I think that one has a little bit different from this one that we're doing, that we did currently in this class.
Yeah, there are two different questions. He sent the question for that one is different from the one we did. The one we did is according to the TQ is last year's test question. And
Okay.
the one he covered in class, I think was the tutorial question he gave them. So and he didn't bring it out in their test. So I don't think he's going to bring it out in our test, but it's always a good idea to know it, sha.
All
Any
right,
other
thank you.
any other questions?
Do you have any like list of problems you feel with the practice to kind of
Mm,
self-develop or problems you worked on like you think we could try solving them?
well,
Help me.
aside the playlist, I don't have any list per se. What I just try to work on are like maybe things that he hinted at in class or like maybe things he asked us to figure out in class. And let's say I just think of a random problem that I feel might come out, like this reverse array, because I know he said something about reversing. I just try to implement it, but I don't have any list per se outside the playlists.
Okay.
Or do you want me to share the code for?
Please,
Oh, I appreciate.
yeah, please say your code for this one we just did.
Just this one, Abby, or the. I've shared the code for this
You
last
can share for both of them.
for both. So basically,
Yeah.
the one that we used multiply without core and the reverse.
Yes, yes.
Uh, okay. I'll share it. That means I'll have to send it to Kunle. I'll share it.
All right, thanks.
Yeah. And one other thing I didn't cover in the Kini, in the test question, he said you should save it in hex file. So I think I've already shown how to save it in hex before. Have I even closed this? So to save in hex, just save as hex code, then specify the name and try to note wherever I'm saving it so that you can zip it together with your assembly language program.
You
So
said there was one like bug or something with the simulator when you're trying to save your hex file. Yes,
yeah, normally, basically what happens is it usually includes the .asm. So by default, it adds .axm because most people when they're saving they'll use .axm. So if you want to save the hex file, what you should do, like if you were to use something like Word and you're trying to change the type of file, let's say you want to save as PDF, it's meant to replace that .x with .pdf. But what it's doing is appending the extension .hex to this .axm. So by the time you save it, you now have reverse array.asm.hex instead of just reverse array.hex. So what I usually do or what I would advise you should do is just save it as whatever it gives you, which should be your matric number anyway. A matric number, question number, the same format it usually uses. So if I save it now, it's going to be in solutions. Then wherever I save it as, you go there and it's not reflecting. Let me save it again. So save export. Maybe because I didn't close it. Let's try to close it.
yeah, I think that's what I was trying to ask. It was not this particular issue with the extension. It was like if you don't close the application, something will see. You mentioned water.
Yeah, to make sure it's saved properly, just close it before your code go and
I like it.
upload officially.
No.
You like it say how?
Like it here. And people are here.
I don't understand.
I get your people.
Your PPK.
Yeah. People are here.
So just to get you correctly, you said you close the simulator before you.
Said they have to spot as
Yeah, after you save it, close it.
like
And most of the time.
they have to.
Victor, please can you mute your mic? So after you save it, you close it. Most of the time, even after you saved it, it's still going to ask, do you want to save it? Just say yes. Then you come to where you saved your hex file, which is this reverse array dot. Sometimes you have to refresh. Like me, I had to refresh my file explorer for the file to show. Then you can just rename it and remove the extra.asm that is not there. But if you are dealing with assembly language program, then the extension is just .asm. I think it works with that one normally. The issue is just when you are saving it at hex. It includes asm on hex. So you might just want to remove the extra asm that is not required. The cylinder code, Kunle has already uploaded it to the drive. It's not the volume. It's already on the drive. All the past questions that I've seen, the code is already on the drive. It's just this one we covered today about stack and reversing that I've not sent yet. Okay, so if there's no other question, I think we can end the meeting now. Good night, everyone.
Thank you.
Good night.
Thank you. Good night.
Those are the claps.
Ayabami.